right, who wants to do it? Who wants to ask the first question? Yes?
Is there gonna be angular separation, in resolution
Yeah,
and
there could be.
diffraction limit, like
Yeah, there could be.
calculations on it? Okay.
No, more along the lines of understanding what they are.
Okay.
I mean, it's more, what do they mean, essentially? And understanding that if you make the telescope bigger, what's that do to the angular resolution? Right, that sort of thing. How does it depend on wavelength? If the wavelength got longer, what would that do to the angular resolution? Does it make it better, does it make it worse? Yes?
For that luminosity graph, will we need to know how the planets change from the bottom left to the upper right?
So you're talking about the HR diagram? I would want you to know for the HR diagram, in general, how it's organized. So in other words, let me find HR diagram here. So I would want you to know that if I don't care if you can determine the valid jump home. That you're plotting luminosity versus temperature. Which way does temperature increase? To the left or to the right? That way, yeah. Which way does luminosity increase? Up, right? So if I were to point right here, stars, if I had a star in this region, what would it be in terms of, would it be dim or bright? Or actually in terms of, would it be low luminosity or high luminosity? Low, because luminosity increases upwards, right? So low luminosity is it low temperature or high temperature? High temperature, right? So this is a high temperature, low luminosity star, and so forth. I'd want you to know where the main sequence is. Not that you have to be able to draw exactly where it is, but you should understand that it snakes from upper left to lower right on the diagram. I want you to know where the supergiants are, where the giants are, where the white dwarfs are, and that sort of thing. And then again, remember too that we did comparisons. In other words, I'd want you to be able to know, based on where stars are on the diagram, which star is larger than the other, if you can tell that. How you can do that sort of thing.
So Barnard star, and then is it Procyon B?
Yeah, so here's Barnard star right here, here's Procyon B right there.
So Procyon B would have they have the same luminosity.
Yep, they have about the
Barnard
same
star,
luminosity because
right.
they're along a horizontal line.
But Barnard star is significantly larger.
Barnard, it would be, as a matter of fact, but I'd want you to know how to deduce that. In other words, how do you know that? So their luminosity is about the same.
Right, because for the luminosities to be the same, Barnard star is significantly less hot. So it makes up for that in surface area.
Right, it has to make up in surface area what it lacks in temperature or flux, so to speak. So in other words, kind of to be, you're right, to be more specific, remember we said that the luminosity is I put it in terms of the surface area of the star times the flux coming from its surface. So if I compare Barnard star and Procyon B here, well, first of all, we said the luminosities are the same for those two stars. L is the same. Which star has the larger flux?
Is flux like temperature?
It's not temperature literally. It isn't temperature. It is the power radiated by each square meter of the surface, the watts coming out of each square meter of the surface. And from the Stefan-Boltzmann law, the flux is directly related to the temperature. The flux is sigma times T to the fourth power, so the hotter one has the bigger flux.
Yeah, Procyon B.
So Procyon B has the higher flux. So here, flux is bigger for, well, that's exactly what I was trying to do. Bigger for Procyon B. So if we stick to Procyon B here, it's got the same luminosity as Barnard's star, but it's got a bigger flux than Barnard's star. So what do we know about its area compared to Barnard's star? It's got to be smaller to compensate for the bigger flux. So the area has to be smaller for Procyon B. So in other words, if you're comparing the two stars, and you want to know which one is bigger, well, we just figured out that Procyon B is smaller, so therefore Barnard's star is the larger of those two stars. That's the kind of comparison I want you to be able to make. If the stars have the same luminosity, but different surface temperatures and therefore different fluxes, be able to use that fact to compare their areas the way we did here and figure out which one's bigger. The other scenario would be if the two stars have similar surface temperatures, but one has a higher luminosity, you can use that to figure out which one is larger. If they have the same surface temperature, then they have the same flux. And then clearly, if they have the same flux, the one with the bigger area has the bigger luminosity in that case. Any questions about that? I'm happy to go over that again if someone wants me to say that again. No takers? Yes?
Why does a single radio telescope have poor angular resolution despite being so big?
So there are two things that go into determining angular resolution, and one of them is the size of the telescope's mirror or lens, and the other is the wavelength of the light that it is detecting. And I use here light in the very general sense, all forms of electromagnetic radiation I'm calling light. So radio waves are light, X-rays are light, they're all just different kinds of light. Visible light is one particular kind of light. So how does it work? If I make a mirror bigger, or a lens bigger, does that improve the angular resolution or make it worse? It improves it. In terms of the number, is improving angular resolution making it a larger number or a smaller number? Smaller, because angular resolution is the smallest angle there can be between two things, and you can still tell them apart. So smaller is better for angular resolution. For fine detail, you want things to be really close together on the sky and still be able to tell them apart. So bigger is better for angular resolution when it comes to diameter of the mirror, but what about wavelength? It's the other way around. Yeah, shorter wavelengths produce better, i.e. smaller angular resolution numbers. So the reason why a radio telescope has poor angular resolution, despite the large size of the dish would help you, but radio waves are very long in wavelength, and that screws you up in terms of angular resolution. The long wavelength is what is responsible for the poor angular resolution of a single radio telescope. And that's why we link it's a reason we link radio telescopes together to make interferometers in order to improve the angular resolution. Any questions about that? Yes?
Could you go over the difference between a reflecting and a refracting telescope?
Yeah, so what's the difference between a reflecting and a refracting telescope? So one is, what is the basic difference? As the name implies, which one of those is going to be the one that uses mirrors? Yeah, a reflecting telescope uses a mirror as its primary light gathering element. That's because mirrors work by reflection. Refractors, on the other hand, instead of a mirror as the main light gathering element, they use a lens, right? And all the world's very large telescopes, are they refractors or are they reflectors? They're reflectors. Why? Well, this slide right here. This is slide 17 in chapter 6 has all that information on it. All the world's leading all the world's largest telescopes are reflectors because they have multiple advantages over refractors, including with a lens, it's got to have high optical quality throughout the lens because the light has to pass through it. So bubbles in a lens will ruin it. You can't use it for astronomical research if it has bubbles in it. Bubbles in a mirror aren't a problem as long as the surface of the mirror is polished nice and to the right curve. Bubbles in the glass underneath the surface don't matter because the light only bounces, reflects off the surface. It doesn't have to pass through the mirror. So that's an advantage. Only the front surface of a mirror needs to be of high optical quality as opposed to the entire volume of the lens. Because light doesn't pass through them, you can support a mirror with a sturdy brace behind it. If you put a bunch of sturdy braces supporting a lens, those sturdy braces would mess up the image. Mirrors don't have chromatic aberration. In other words, they don't have the fact that, unlike lenses, lenses have chromatic aberration. That means different wavelengths of light have slightly different focal lengths. And so as a result, not all the light is brought to a focus at the same point. Mirrors don't have that problem because the law of reflection doesn't depend on wavelength, whereas refraction actually depends on wavelength. Different wavelengths are refracted different amounts by glass. And also, glass absorbs ultraviolet and infrared light over large parts of the infrared and ultraviolet parts of the spectrum. Mirrors can work further into the ultraviolet and infrared because of the fact that the light doesn't pass through the glass, and so it's not absorbed on its way through the glass when it's ultraviolet or infrared. Visible light is, glass is very good at passing visible light, but not so great at ultraviolet and infrared light. So those are the reasons right there. And I don't mention it here, but this is it's also tied to cost as well. It's cheaper to make a large reflector, but that's because you don't have to have high optical quality in all of the glass of the mirror. You don't have to support it from the side. You can support it with big braces underneath. Things like that make it cheaper also to make reflectors and refractors of the same size in general. Yes?
Can you go over arc minutes and arc seconds?
Yeah, arc minutes and arc seconds. That's not too bad, really. You just have to remember that, and you can think of it in terms of, you can remember it from what you know about a clock. You know, think of a minute of time. Think of an hour of time. How many minutes are in that hour? 60. Think of a minute of time. How many seconds are in that minute? 60. So how many seconds are in 1 hour? 3,600, because it's 60 times 60, 3,600. No, you're just a genius. You just multiplied it in your head.
I had it, but I didn't.
You did, but yeah, it's not too hard to do. 60 times 60 is 6 times 10 times 6 times 10. So it'll be 6 times 6 times 10 times 10. 36 times 100, 3,600. Anyway, arc minutes and arc seconds are named by analogy. They're angle, they're not time, but 1 degree of angle, by definition, triple equals means by definition, is 60 minutes of arc. That prime symbol there, which is the same thing you would use to say feet if you were talking about measurements, but that's not what it means here. 60 minutes of arc in 1 degree of angle, and 1 minute of angle is 60 seconds. Seconds of arc, also called arc seconds, arc minutes. Seconds of arc, of angle. So there are 60 seconds in a minute of angle, there are 60 minutes in a degree of angle, and therefore 1 degree is 3,600 seconds of arc. 3,600 arc seconds, seconds of angle. So in other words, an arc second is 1/3,600th of a degree, a tiny little angle. The moon is about half a degree in angle in our view from Earth. that means it's about 30 minutes of arc in angle, because half a degree is 60 minutes, so half a degree is 30 minutes. The angular resolution of the human eye is about 1 minute of arc, roughly speaking. So you can see angles that are about 1/30th of the size of the moon in the sky. That's how sharp your vision is. There are birds of prey that have much better vision than we do because the cells in their retinas are packed more closely together. And so I think I mentioned in class that there are birds of prey that can see craters on the moon, which would be cool, but I don't think they appreciate it. You know, they don't look at the moon and think, wow, I can see craters. Those must be impact scars from the early bombardment in the solar system after it formed. I don't think birds think that. So does that do it? Okay.
So there are 60 minutes of arc in 1 degree and 3,600 seconds.
And 3,600 seconds, just like there are 60 minutes of time in an hour and 3,600 seconds of time in 1 hour. Yep. Yes?
Could you go over flux freezing? Yeah. No.
We're, yes, I can.
Okay.
Was that your question too, or you, okay, that's fine. I can guess yours next. So, can we go over flux freezing? Sure, we can do that. So, flux freezing, we use that to explain what phenomenon? That's associated with sunspots. Flux freezing is about sunspots. So, in particular, the idea with flux freezing is that the plasma, if you have plasma that has magnetic field lines threading it, first of all, what's plasma? There's the word
Hot
plasma.
gas.
Ionized gas, basically. Ionized gas is a plasma. The sun is hot enough that many of the atoms have electrons stripped off of them. That's what we mean by a plasma in the sun. It's not the same thing that we mean by blood plasma. That's a different thing. The plasma in the sun means it's ionized gas. That means that there are free meaning free to move, not attached to an atom, free electrons in the sun's plasma, and ions, atoms that have lost some of their electrons, both of which can flow around to form electric currents. So the sun's plasma is an electrical conductor. Flux freezing refers to the idea that the magnetic field lines and the plasma move together. If the plasma moves off to the right, then the magnetic field lines that are threaded in that plasma also move off to the right. If the plasma moves, it drags the field lines along with it. That is what flux freezing means, is that plasma and magnetic field lines move together. And it's ultimately because of the currents that flow in the plasma if the plasma tries to move without the field lines following it. It's due to electric currents. I don't expect you to understand the details of that, but it's due to magnetic fields created by electric currents flowing in the plasma. So that's what flux freezing itself is, but then you can't really talk about that and leave out the next part, which is there's also what we call magnetic tension. Those electric currents that create flux freezing by creating additional magnetic field, they also feel, the need to sneeze, they also feel, where that came from, they also feel forces due to the magnetic field, and that ultimately leads to a phenomenon called magnetic tension, where the magnetic field lines kind of don't like being bent, like guitar strings or violin strings or rubber bands. They quote unquote don't like being bent. If you bend them, they pull back on you. The magnetic field lines pull back on the plasma if the plasma distorts them, if the plasma bends them away from being straight. And how strong a magnetic field resists being bent depends on how strong the magnetic field is. In a weak magnetic field, the field lines are not under high tension, and so it's easy for the plasma to move them around. In a strong magnetic field, the field lines are under high tension. They become very stiff, and it's very hard to move them around. And that's key to understanding, next slide, that's key to understanding what makes sunspots cooler than their surroundings. It's a combination of magnetic tension and flux freezing. But first I will pause here to ask if there's any questions about this. Yes?
It has to do with sunspots,
Mhm.
but it's more the sunspot cycle, like the 11-year and.
Yeah, I'll get you in just a minute, but I wanted to complete the cycle, so to speak. Well, not the cycle, I want to complete this one. So, if we combine those two concepts, flux freezing and magnetic tension, we can understand why sunspots are cool. Sunspots are cool because you don't have convection inside the sunspot. Outside the sunspot, we have this convection pattern, and you better remember what you call that. It's the solar GR, are the first two letters of the word. The solar what? Nobody? So this stuff. The solar granulation is the tops of convection cells in the sun's outer atmosphere. Inside the spots, it shuts off that convection. The magnetic field shuts off that convection because inside the spots, the magnetic field is very strong, several thousand times stronger than outside the spots. So the magnetic field lines are very stiff. They don't let themselves be bent very much at all. It's very hard to bend them. And that means that the plasma inside a sunspot can't move side to side, because if it moves side to side, flux freezing would say that it has to drag the magnetic field lines with it, but the magnetic field lines are very stiff, so they don't let themselves be moved very much. And so as a result, you don't have convection inside the sunspot. You don't have that overturning granulation inside the sunspot, but convection is how you transport mostly how you transport energy in the sun's photosphere. And so if you turn off convection inside the sunspot, you don't get as much energy coming into it from below as in the surrounding areas, and so it becomes cooler than the surrounding areas and thus darker than the surrounding areas. And that's essentially how sunspots work. The strong magnetic field is very stiff, it won't let itself be pushed around side to side, and so convection stops inside the spot, and that keeps energy, that greatly reduces how much energy can come into the spot from below, because convection is how energy is mostly transported in the sun's outdoors. So, any questions about that, including wood? Can you say that again? Yes?
Sorry, are the location of the sunspots determined by the magnetic field lines?
They are. Sunspots are where magnetic field lines kind of pop out of the solar surface. There's, if you look underneath the solar surface, you would find that the magnetic field lines wrap around it. This is part of the sunspot cycle understanding that we have. Magnetic field lines wrap around it in kind of ropes of magnetic flux. We say there are flux ropes wrapped around the sun, and at points where they kink, they can stick out of the sun's surface, and sunspots form where those arches of magnetic field intersect the photosphere, intersect the solar surface, because you need those vertical, the magnetic field lines in spots are vertical. In other words, they're sticking perpendicular to the surface, and that's what suppresses that side-to-side motion. So the locations of the spots are determined by where those kinks, so to speak, form in the sun's magnetic field that wraps around the sun during the sunspot cycle. What was your question going to be?
It was just about if you could go over the 11-year sunspot cycle and then the 22-year magnetic cycle.
Yep, so 11-year sunspot cycle, 22-year magnetic cycle. So first of all, the sunspot cycle is a cycle literally in how many spots are on the sun's surface, how spotted it is. It reaches a maximum about once every 11 years. It varies. Sometimes it's a little less than 11 years, sometimes it's been more than 11 years, but on average there's 11 years between maxima of the sunspot cycle. At sunspot maximum, the sun is maximally covered with spots compared to at other times. So this plot right here shows between about 1900 and 2010 the number of sunspots, percentage of the sun's surface covered by sunspots as a function of time. And so sunspot maximum corresponds to where the peaks are. And you can see that it keeps going from a minimum to a maximum to a minimum to a maximum to a minimum. And the time between the maxima is about 11 years on average. That's the sunspot cycle. The thing is, there's a 22-year magnetic cycle because the orientation of the sun's magnetic field lines flips from one sunspot cycle to the next sunspot cycle. And in particular, look carefully at the direction that the magnetic field lines are pointing in this first figure here. This is a time of solar minimum. The sun's magnetic field has this simple kind of north to south configuration at times of solar minimum. So here's a solar minimum. Which way are the arrows pointing on the magnetic field lines, up or down? Pointing up, right? They're pointing up here. Here is the representation of the next solar minimum. Which way are the magnetic field lines pointing? Down. Now, the cycle will repeat again. The field lines will get twisted around again, form kinks. When there's a maximum amount of kinking happening, there's a maximum amount of sunspot activity, but it fades back to a minimum again. What do you think the magnetic field will look like at the next sunspot minimum after this one? The field will be up again. And then the next one after that, down again. So in other words, the point is that from one sunspot minimum to the next sunspot minimum, or also from one sunspot maximum to the next sunspot maximum, the magnetic field line has reversed its overall direction. So there is an 11-year cycle in the number of spots, but a 22-year cycle in the magnetic field, because to get back to the original configuration again, you have to go through 2 sunspot cycles. In other words, here is 11 years later, we've gone through one sunspot cycle, the magnetic field went from up to down. We'll have to go another 11 years to flip this back to up again. So the next time the sun looks like this is 22 years later, 2 minima later, because of the fact that you flip with every cycle. Kind of like, here's this card that is advertising Hamlet on April 12th, 13th, and 14th. Here's one side of the card, here's the other side of the card. So let's suppose I flip this card once every second. So 1001, flip, 1001, flip, 1001, flip. I'll put it so you guys know. 1001, flip, 1001, flip, 1001, flip, 1001, flip. How often is it flipping? Once every second, right? How often do you see Hamlet as opposed to the blank side? 1001, 1001, 1001, 1001. How many seconds between when you see Hamlet again? 2 seconds. Because you got to flip twice to get back to seeing Hamlet again. So even though the card is flipping once every second, you have to go through 2 flips, 2 seconds to see Hamlet again. Similarly with the sun, you got to go through 2 minima to get back to the same configuration that we started with this one. So this is 11 years later, and then 11 years after that, 22 years after we started, we'd be back to that configuration. Does that make sense? That's the idea there. Yes?
Why does the equator of the sun rotate faster than the poles of the sun?
That isn't fully understood. So my smart aleck answer is because it can't. In other words, which isn't the actual answer. Okay, that's not a good answer, but it's part of it. In other words, Earth couldn't do this because Earth is a solid body. So there's no way the equator could go around faster than the poles for Earth. But the sun isn't a solid body. The sun is gaseous throughout. Okay, it's plasma throughout. But in other words, it's not a solid body. And that gives it the possibility of rotating differentially. The physics of exactly why the equator rotates faster than the poles is complicated. And there's some evidence that some stars have what is called anti-solar differential rotation, which is a mouthful. But in other words, there's some evidence looking at spots on other stars that that's the other way around for them, that the poles go around faster than the equators. That the period for one rotation of the poles is less than for one rotation of the equator. So the answer is, I don't know a simple way to explain why, but fundamental is the fact that it can, that it's gaseous, and so at least that is a possibility, but it's complicated. Translation, I'm not going to ask you on the exam to explain it. It's hard. Yeah.
Can you just go over a little bit again about how it's different from the 22 magnetic cycle?
So the sunspot cycle is when the number of spots peaks every 11 years. Okay? So here's a solar maximum right there. Okay? Let's suppose that at this solar maximum, the magnetic field lines, where did it go? The magnetic field lines were, so this would represent a time of solar maximum here, when there's lots of twisting and kinks and all that. So there's two possibilities for a solar maximum, right? So for a solar minimum, you can have the field lines are just pointing up or pointing down overall. Solar maximum, you can have, notice that in the poles, you still have field lines pointing up at the sun's north and south poles. And then on top of that, you can have where the sunspots are on the north side of the equator, north magnetic field out in front, south magnetic field behind, and vice versa on the other side there. At the next maximum, if I would draw exactly the same figure, except all the arrows would be in the other direction. So that this arrow would look like this. What kind of spot would this be? Would it be north or south, the next maximum?
South.
It would be south, and this one would be north, and this one would be north, and this one would be south. Everything switches. So from one maximum to the next maximum, everything switches, magnetically speaking. And so that means if we look at this plot here, maybe this, and I don't know for sure, but let's suppose this maximum right here had the magnetic field that looked like it did in the figure that's actually there that I just showed you. Then this maximum will be the other way around. And this maximum will be back to that first way again. And this maximum will be the other way around. And this one will be like that first one again. So in other words, going from maximum number of spots to maximum number of spots is 11 years, but I gotta go another 11 years because it's every other maximum that has the same configuration as the one that I started with. So 22 years to go to the same kind of magnetic maximum again.
Makes sense.
Yes?
When you do an equation that was on the Master in Astronomy, it's the one that gave like the Earth's distance from the sun and then the sun's apparent brightness, and then it asked like what's the apparent brightness if you're like half the distance from the sun
Yep.
or 5 times. Can we do
Right.
one of those?
We certainly can. And that one was easier than it might have looked at first. So in other words, the real key there, so if all I told you was the sun has a certain luminosity, and I wanted to figure out what is the brightness a certain distance from the sun. So the formula is that brightness equals luminosity divided by the area of a giant sphere whose radius is equal to the distance to that source of luminosity. So I could give you the number for the sun's luminosity, which is 4 times 10 to the 26 power watts. And I could give you the distance of some planet from the sun in meters. And then you could whip out your calculator and divide the sun's luminosity by 4 pi times that distance in meters squared, and that would give you the brightness of the sun from that location in watts per square meter, and that would be great. But that's not really the point of that problem. So they just told you, and they mixed up the numbers for different people, so people can't just say, hey, what'd you get, you know, right? But so for example, I saw in mine, because it actually mixes up numbers for me too when I looked at it, I think it said the sun's brightness is about 1,300 watts per square meter, which is about right. It's actually like 1,376 watts per square meter, which at Earth's surface. By the way, just as an aside, that would mean, okay, suppose I had a solar collector that was 100% efficient. It gathered all of the light falling on it from the sun, and it was 1 square meter in size, held perpendicular to the beam of light from the sun so it could gather as much light as possible. Then you could get 1,376 watts out of that. Can you name me something that requires about 1,376 watts of power, roughly speaking? It makes way more than that. A nuclear reactor makes like many megawatts of power, many millions of watts. I'm thinking of an everyday household item that you have probably used before, or you know somebody has used, something that's about, say, 1,500 watts. Not bad. I'm thinking of something else. Yeah, microwaves are like, so yeah, not bad at all. Okay, we'll go with that. A kitchen microwave's around 1,700 watts if it's a very powerful one. Some of them are 1,100 watts. So yeah, good example. The sun's brightness at Earth is such that it's about one microwave oven power's worth for every square meter of Earth's surface. So that's, I like it, good, perfect. That's just as good as what I was thinking of.
What are you thinking of?
I'm thinking of, I just got out of the shower. Man, is my hair dry. I'm in a hurry. Hair dryer's about 1,500 watts too. So I like to think of the sun's brightness at Earth as approximately 1 hairdryer per square meter, just to kind of put it in kind of everyday terms. Because you hear 1,500 or 1,376 watts, what's that? It's a hairdryer or a microwave. Not bad. Yeah, a microwave or a hairdryer per square meter. Anyway, back to our story. The brightness is, say, 1,300 watts per square meter, and let's say that we moved, what if we moved Earth, I forget what it said exactly, you said like 5 times closer to the sun, was that it? Or, yeah. We moved Earth 5 times closer to the sun. What would the new brightness be? So, your first thought might be, okay, I know the sun's luminosity, I'll figure out how many meters is 5 times close to the sun and plug in this formula again, but that would be too much work because this is an inverse square law. It depends on 1 over the distance squared. Whatever I do to the distance, whatever factor I change the